This is an example of classification of an input image. The model accepts images resized to 299 by 299. We also performed rudimentary localization. We first classify the entire image. In this case, the image is green. Then divide the image into a grid of 16 tiles, 4 in this example. Each tile is then classified, in this case classified as 2 red and 2 green tiles. The tiles that match the overall image classification are then highlighted, the 2 green tiles, and then the image is then reconstructed. This is demonstrated here, some improved localization techniques. This video classification example uses smoking scenes from Hollywood movies. Over the course of this example, smoking is identified correctly about 80% of the time. Another usage for smoking detection could be automating film age restriction ratings for smoking content. For example, PG-13 only allows a certain amount of tobacco use over the runtime of a film. We also smooth our video classification results. Demonstrated here, we take the current frame and then add it to the 14 previous frames in a frame buffer. We then take the mode of the frame classifications in our cartoon example. 3 of the 5 frames are classified as green, so that's our mode. We then take the mean of the mode probabilities, and then that forms our current frame classification. We have higher error, up to 70% when testing with crowds. This footage is from a Sony demo tape of New York City in 1993, and it demonstrates a lot of erroneous cell phone calling, which wasn't common at that time.
I will discuss the process to increase the brightness of dark images in our training data to increase the accuracy and efficiency of classification. The first step is to find these dark images. First, we should convert the images to grayscale, and then compare the gray value of each pixel with the preset value. If the former is smaller than the latter, then the pixel can be seen as a dark pixel. In a similar way, if the proportion of the dark pixels in an image is greater than a threshold, the image can be seen as a dark image. After several attempts, I believe that 30% will be a good threshold. The first picture is the original images, and the second picture is the dark images we get from the original images. Next step is to enhance the brightness of the dark images we get. I think we can also use the KIND network. This model has a special module which called a multi-scale illumination attention module. That module can alleviate visual defects left in KIND. By loading these pre-trained checkpoints, we can enhance the brightness of pictures.
Hello, I am Alexander Mohesi, and this is CVDancer's video report. I would just like to step through some of the more interesting features of our training code. We begin by setting up our parameters, such as our initial learning rate and our image parameters. We then see our first interesting feature, which here is the cosine decay learning rate scheduler, which hooks directly into the optimizers from Keras and will slowly decrease our learning rate over the first 10 epochs. This will allow us to train very quickly while avoiding loss of accuracy due to excessive learning rate later on. Now, the second thing we see is our inception V3 algorithm. We exclude the top layer, which is fully connected, so that we can have our 8x8 by 2048 tensor, which we then use an average pooling layer and flatten layer to flatten into a vector that we can feed into our softmax layer, which puts out one of 4 categories, which is how we are doing our categorization.